Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Asad Abbas. In this lecture, we will continue our discussion on quality assurance activities and defect management perspective. In the previous lecture, we had discussed one quality assurance alternative, that is defect prevention. In this lecture, we will discuss the other two quality assurance alternatives, that is defect reduction and defect containment. So we start our discussion with defect reduction. For most large software systems in use today, it is unrealistic to expect the defect prevention activities discussed previously to be 100% effective in preventing accidental fault injection. Therefore, we need effective techniques to remove as many of the injected faults as possible under project constraints. In fact, there are several techniques that are used for defect reduction in software systems, and we will discuss a few here that mainly include the first one is inspection. That is, here we are concerned with direct fault detection and removal, whereas the second technique is uh, testing, where we focus on failure observation and removal of faults, and we will also discuss some other techniques for defect reduction. So we first discuss inspection. Software inspections are in fact critical examinations of software artifacts by human inspectors and are aimed at discovering and fixing faults in the software systems. Inspection is a well-known quality assurance alternative familiar to most experienced software quality professionals. The earliest and most influential work on software inspection was presented by Ph.D. in 1976, which is also known as Ph.D. inspection these days. In fact, there are several basic ideas or thoughts about inspection, and these include, for example, inspections are critical reading and analysis of software code or other software artifacts such as design, product specifications, test plans, etc. Similarly, inspections are typically conducted by multiple human inspectors through some coordinated process. Multiple inspection phases or sessions might also be used for performing the inspection activities. Then the faults are detected directly in inspection process by the human inspectors, either during their individual inspections or various types of group sessions. Then the identified faults, that is the faults that are identified during the inspection, they need to be removed as a result of the inspection process, and their removal also needs to be verified through some auditing activity. The inspection processes in fact vary, but typically include some planning and follow-up activities in addition to the core inspection activity. Then the formality and structure of inspections, they may also vary from very informal reviews and walkthroughs to fairly formal variations of like field inspections to the correctness inspections approaching the rigor and formality of formal methods. In fact, inspection is most commonly applied to code, but it could also be applied to other artifacts such as requirement specifications, design, test plans, test cases, user manuals, and other documents or software artifacts. Therefore, inspection can be used throughout the development process, particularly early in the software development, before anything can be tested. Consequently, inspection can be an effective and economical quality assurance alternative because of the much increased cost of fixing the late defects as compared to fixing at earlier stage. Then the second technique for fault reduction is testing. Here our focus is on failure observation and fault removal. In fact, testing is one of the most important parts of quality assurance activities and the most commonly performed quality assurance activity. Testing involves the execution of software and the observation of the program behavior or outcome. If a failure is observed, the execution record is then analyzed to locate and fix the faults that caused the failure. So mainly there are two types of testing which include black box testing and white box testing. In black box testing, a program or system is executed and its behavior is observed against some inputs. Whereas in white box testing, the structure or the code of the software system is observed or analyzed to determine if there are any problems with the code or structure of the system. Regarding testing, it is also important to discuss that when can a specific testing activity be performed and related faults be detected. Because testing is an execution-based quality assurance activity, a prerequisite to actual testing is the existence of the implemented software, units, components, or the systems that are to be tested, although preparation for testing can be carried out in the earlier phases of software development. For example, during the requirements engineering phase, the testing team that can also start working on preparing the test cases. As a result, actual testing can be divided into various subphases, starting from the coding phase up to post-release product support, including, for example, unit testing, component testing, integration testing, system testing, acceptance testing, and beta testing, etc. The observation of failures can be associated with these individual subphases, and the identification and removal of related faults can be associated with the corresponding individual units, components of the complete system. If software prototypes are used, such as in the spiral process, or if a software system is developed using an incremental or iterative process, then testing can usually get started much earlier. Later on, integration testing plays much more important role in detecting the interoperability problems among different software components. Moreover, regarding the testing activities, it is also important to know that what to test and what kind of faults are found. As I mentioned in the previous slide, that the testing comprises of uh, two types, mainly the black box testing and white box testing. Black box or functional testing verifies the correct handling of the external functions provided by the software, or whether the observed behavior conforms to the user expectations or product specifications. On the other hand, white box or structural testing verifies the correct implementation of internal units, structures, and the relationships among those structures. Various techniques can be used to build models and generate test cases to perform systematic black box or white box testing. When black box testing is performed, failures related to specific external functions can be observed, leading to corresponding faults being detected and removed. Here in black box testing, the emphasis is on reducing the chances of encountering functional problems by the target customers. On the other hand, when white box testing is performed, failures related to internal implementations can be observed, leading to corresponding faults being detected and removed. Here in white box testing, the emphasis is on reducing the internal faults so that there is less chance of failures later on, no matter what kind of application environment the software is subjected to. It is also important to determine that when or at what defect level one needs to stop testing. In fact, most of the traditional testing techniques and testing subphases use some kind of coverage information as the stopping criteria, with the implicit assumption that higher coverage means higher quality or lower level of defects. For example, checklists are often used to make sure that major functions and usage scenario are tested before product release. Every statement or unit in a component must be covered before subsequent integration testing can proceed. More formal testing techniques include control flow testing that attempts to cover execution paths and domain testing that attempts to cover boundaries between different input subdomains. Such formal coverage information can only be obtained by using the expensive coverage analysis uh, and some other testing tools. On the other hand, product reliability goals can be used as a major objective criterion to stop the testing activities. The use of this criterion requires the testing to be performed under an environment that resembles the actual usage by by the target customers so that realistic reliability assessment can be obtained. That actually results in the usage-based statistical testing. The coverage criteria ensures that certain types of faults are detected and removed from the code, thus reducing the overall defect level in the system. The usage-based testing and the related reliability criteria ensure that the faults that are most likely to cause problems to the customers are more likely to be detected and removed, and the reliability of the software reaches certain targets before testing stops. In addition to inspection and testing, there are also other techniques for error detection and reduction. These include static analysis techniques, dynamic execution based techniques, and in-field measurement and analysis. The static analysis techniques, besides inspection, include various formal based analysis such as algorithm analysis, decision table analysis, boundary value analysis, finite state machines, pattern net modeling, and uh, Similarly, control and data flow analysis and software fault trees, etc. Similarly, in addition to testing, other dynamic execution-based techniques also exist for fault detection and removal. For example, symbolic execution, simulation, and prototyping can help us detect and remove various defects early in the software development process before large-scale testing becomes a viable alternative. On the other hand, in-field measurement and related analysis such as timing and performance analysis for real-time systems and accident analysis and reconstruction using software fault trees and event trees for safety critical systems can also help us locate and remove the related defects. Although these activities are an important part of product support, they are not generally considered as a part of the traditional quality assurance activities because of the damages already done to the customer's application and to the software vendor's reputation. Because of the benefits of dealing with problems before product release instead of after product release, the focus of these activities is to provide useful information for future quality assurance activities. Fault distribution is highly uneven for most software products, regardless of their size, uh, functionality, the implementation technologies or languages, and other characteristics. In fact, much empirical evidence has accumulated over the years to support the 80-20 rule, which states that 20% of the software components are in fact responsible for 80% of the problems. So these problematic components can generally be characterized by specific measurement properties about their design, size, complexity, change history, and other product or process characteristics. Because of the uneven fault distribution among software components, there is a great need for risk identification techniques to analyze these measurements data so that inspection, testing, and other quality assurance activities can be more effectively applied on those potentially high defect components. Then the third quality assurance alternative we discuss here is defect containment. Because of the large size and high complexity of most software systems in use today, the defect reduction activities that we just discussed can only reduce the number of faults to a fairly low level. But in fact, these techniques they cannot eliminate these defects completely. For software systems where a failure impact is substantial, such as many real-time control software subsystems used in medical, nuclear, or transportation and other embedded systems, this low defect level and failure risks may still be inadequate. Therefore, some additional quality assurance alternatives or activities are needed to handle such situations. Moreover, these few remaining faults they may be triggered under rare conditions or unusual dynamic scenarios, making it unrealistic to attempt to generate the huge number of test cases to cover all these conditions, or to perform an exhaustive inspection based on all the possible scenarios. Instead, some other means need to be used to prevent failures by breaking the causal relationship between these faults and the resulting failures, thus tolerating these faults or to contain the failures by reducing the now resulting damages. So here we will discuss few techniques for fault tolerance and failure containment. Software fault tolerance ideas originate from fault tolerance designs in traditional hardware systems that require high levels of reliability, availability, or dependability. In such systems, spare parts and backup units are commonly used to keep the systems in operational conditions, maybe at a reduced capability. But still, the good thing is that these systems are still able to execute and perform some operations. The primary software fault tolerance techniques include recovery blocks, similarly N-version programming, which is also known as NVP, and some other variations. So we will discuss the recovery blocks and N-version programming here briefly. Here we will discuss the defect containment techniques, which include recovery blocks and N-version programming. Recovery blocks use repeated execution or redundancy over time as the basic mechanism for fault tolerance. If dynamic failures in some local area are detected, a portion of the latest execution is repeated in the hope that this repeated execution will not lead to the same failure. Therefore, local failures they do not propagate to the global failure, although some time delays may be observed or expected in that situation. Then N-version programming. N-version programming, which is also known as multi-version programming or multiple version dissimilar software, is a method or process where multiple functionally equivalent programs are independently generated from the same initial functional specifications. The concept of N-version programming was introduced with the notion that the independence of programming efforts will greatly reduce the probability of identical software faults occurring in two or more versions of the program. The aim of the N version programming is to improve the reliability of the software operations by building or by introducing fault tolerance in the system. The general steps, in fact, there are some steps that are performed in N version programming, and the first step is that an initial specification of the intended functionality of the software is developed. The specification should unambiguously define the functions, data formats, cross checkpoints, comparison algorithms, and responses to the comparison algorithms. Then, in the next step, from the specification, two or more versions of the program are independently developed or generated, each by a group that does not interact with each other. The implementation of these functionally equivalent programs use different algorithms and different programming languages. At various points of the program, special mechanisms are built into the software which allow the program to be governed by the N version execution environment. After that, an N version execution environment is developed which runs the N version software and makes final decision of the N version programs as a whole given the output of each individual N version program. The implementation of the decision algorithms can in fact vary, ranging from as simple as accepting the most frequently occurring outputs. For instance, if a majority of versions agree on some output, then it is likely to be correct, or to some more complex algorithms. So that's all about our discussion on quality assurance and defect management. Mainly, we discuss the three types of techniques for defect management, that is, defect prevention activities, defect reduction activities, and defect containment activities. So the aim of the defect prevention activities is to prevent the defects in the software systems by introducing some mechanisms that help the development teams to prevent those errors. For example, education and training that might be an impressive or effective defect prevention technology. Similarly, by breaking the causal relationship between the errors or faults and their sources, that may also reduce or help us prevent the errors. Then defect reduction techniques, they mainly include some inspection and testing based activities, whereas the purpose of the defect containment techniques is to avoid the propagation of the defects or problems in the software systems globally. So the two techniques for defect containment that we discussed here in this lecture, they include recovery blocks and N version programming. The materials in this video are based on our course book titled Software Quality Engineering, Testing, Quality Assurance, and Quantifiable Improvement by Jeff Tian. For more details, you can consult the book. Thank you.